Picture this. You're blindfolded, standing in an infinite, pitch-black, incredibly hilly landscape. Your sole objective? Find the absolute lowest point in this entire world. If you just take a step downhill, you might find a valley, sure, but how do you know it's the lowest valley and not just a small crater on the side of a massive mountain? Well, in the world of machine learning, algorithms face this exact dilemma every single second. Today in this explainer, we are going to illuminate the magical math that actually solves this problem: convex optimization.
All right, here's our roadmap for today. We're going to hit the magic of convexity, dive into sets, functions, and bowls, tackle linear and quadratic programming, unlock the power of duality, break down Fenchel conjugates, and finally see how all this powers machine learning. Let's get right into it.
Starting off with Section 1, the magic of convexity, basically the easy button for optimization.
So you know that in optimization, we're always hunting for the absolute best answer out of, well, infinite possibilities. But algorithms, they're kind of short-sighted. How do they actually find that global best answer without getting stuck? I mean, if an algorithm is just blindly walking downhill in this wavy, crazy mathematical landscape, it's super easy for it to get trapped in a local minimum. It thinks it's at the very bottom, but the true global minimum is actually hiding behind the next hill over.
Right, so this is where convexity comes in. And it's honestly like magic. When we're dealing with the convex optimization problem, our landscape isn't this chaotic mess of unpredictable hills and craters, nah. It's shaped more like a single, perfectly smooth bowl. And because of that specific shape, we get an absolute mathematical guarantee. Any local valley you stumble into, it is mathematically guaranteed to be the absolute lowest point, the global minimum. It's literally an algorithmic easy button.
Moving to Section 2, sets, functions, and bowls, the geometry of optimization. Now, if the dense algebra of all this looks intimidating, don't worry. Shifting our perspective to geometry makes it so much more intuitive.
Take a look at this. The rule for a convex set is actually really simple. If you pick any 2 points inside a shape and draw a straight line between them, that entire line segment has to stay completely inside the shape. You can see the green shape on top there. That's a convex set. But look at the red, kind of heart-like shape below it. If you connect those 2 upper lobes, the line totally leaves the boundary. Boom, that makes it a non-convex set. And you know, this whole geometric concept applies beautifully to functions too. A convex function basically looks like a sagging rope or, a bowl. The really cool geometric truth here is that if you draw a tangent line at any point, like that dashed orange line at x equals 2, it is always going to lie completely below the curve. It perfectly cradles the function, acting as a rock-solid lower bound.
Okay, Section 3, linear and quadratic programming. Let's see what happens when we start building walls around our perfectly smooth bowl. Because let's face it, in the real world, we rarely have unlimited options.
We always have constraints, right? Budgets, time limits, physical bounds. So depending on the shape of our problem, we rely on 2 massive heavy hitters: linear programming and quadratic programming. Both deal with linear constraints, meaning our walls are flat, straight lines, but they differ in their core objective. Linear programming uses a perfectly flat, tilted plane as its objective, whereas quadratic programming, it introduces these curved bowl-like functions that create elliptical contours.
To put this into perspective, just think of a real-world factory. Say a company wants to absolutely maximize its profit by producing a bunch of different products. They can't just magically produce infinite goods, right? They're constrained by limited raw materials, limited labor, the usual stuff. So figuring out the absolute optimal production plan without breaking those hard resource constraints, that is exactly what linear programming solves.
And if you look at the geometry of it, notice how those linear constraints act like a series of intersecting walls. They fence in this shaded area, which we call the feasible region. And here's the kicker. Because both the objective and the constraints are completely linear, your optimal answer is practically always going to be pinned right into one of the extreme corners of that shaded shape.
Now contrast that with a quadratic program. Those straight walls, our linear constraints, they still create that shaded feasible region. But the objective function? It creates these curved elliptical contour lines, kind of like topographical rings on a hiking map. We're essentially trying to find the very center of that bowl, but we're strictly confined to searching only within that shaded area.
Which brings us to Section 4, the power of duality. Because sometimes an optimization problem is just way too mathematically messy or high-dimensional to solve head-on.
Luckily for convex problems, we get to enjoy something called strong duality. As this quote perfectly sums it up,
The optimal solution of our original, or primal problem, is exactly identical to the optimal solution of a secondary, dual problem. This is huge. It means we can safely flip our entire perspective, completely change the math, and still not lose the right answer. How wild is that?
So in simpler terms, duality lets us essentially trade our original variables for constraints. We use these things called the Lagrange multipliers, which are basically mathematical penalties to pull the constraints directly into our objective function. By doing this, we turn a brutally tough minimization problem into a much, much easier maximization problem. It's kind of like looking at the exact same physical object, just from a totally different angle that suddenly reveals the solution in half the time.
All right, Section 5, Fenchel conjugates explained. Let's dive into another powerful perspective shift that's super closely related to duality, where the geometry gets, honestly, truly elegant.
Traditionally, we describe a curve by plotting its individual points on a graph. But the Fenchel conjugate says, hey, why not describe the curve by its slopes instead? Because it's a convex bowl, we can describe it entirely by the infinite family of tangent lines that perfectly cradle it from below. We are literally swapping out the physical points in space for the slopes of the lines touching those points.
And when you derive the conjugate of a quadratic function, you can just use basic calculus. By taking the derivative and setting it to 0 to find the maximum, we seamlessly transform our primal quadratic variable right into its dual counterpart. It mathematically solidifies this incredible idea that a convex function can be completely understood just by looking at its tangent slopes.
Finally, Section 6, Powering Machine Learning, the engine in action. Now you might be asking yourself, okay, why does all this dense math actually matter to me? Well, because this is the direct, beating engine powering artificial intelligence.
The machine learning algorithms you hear about literally every day, they are just convex optimization tools wearing a clever disguise. Drawing a simple line of best fit through data? That's just unconstrained convex optimization. Training a support vector machine to classify images? That's actually a quadratic programming problem. And if you want a model that naturally ignores useless data, what we call L1 sparsity, you're secretly just solving a linear program. It's all connected.
Take ordinary least squares, or OLS regression, for example. Its cost function, the sum of its squared errors, literally forms a convex bowl. And because of that magic of convexity we talked about earlier, the very second the algorithm finds a flat spot, a null gradient where the slope hits 0, it can just stop searching. It is absolutely guaranteed to have found the absolute best global minimum fit for that data.
And this brilliantly illustrates why that mind-bending concept of duality is so incredibly crucial in machine learning. Take a support vector machine. Let's say you're analyzing data with millions of features, massive input dimensions, but you only have a few hundred examples. Solving that normally, it would completely crash your computer. But by swapping to the dual form, the math resizes to match the number of examples, not the dimensions. You compute the exact same optimal answer just in a fraction of the time. At the end of the day, convex optimization takes the blinding complexity of the real world and molds it into these solvable, reliable geometric bowls. It turns what should be an impossible search for perfection into a guaranteed mathematical certainty. So, the next time you use an AI tool, try to look beneath the hood. Knowing the elegant, convex landscapes guiding that algorithm in the optimal answer, how will you use these simple geometric rules to navigate the complex data landscapes of your own future?